This is the Prosthetic Footshell project, sponsored by QL Plus and the Mechanical Engineering Department at Cal Poly SLO. The main goal of this project was to create a new footshell. Users of prosthetic legs have issues with current footshells wearing out too quickly and needing to be replaced too often. They need a more durable footshell that will last longer than commercially available options. Our challenger, Dana Cummings, an ex-Marine who lost his lower leg, found that his footshells were wearing out very quickly. He is a very active individual, and so his footshells would last him around 2 to 3 months, while a typical user's shell is supposed to last around 1 year. Our team was tasked with creating a footshell to last him at least a year. When coming up with a solution, we had 3 major parts to our design process: ideation, manufacturing, and testing. In the ideation stage, we brainstormed and created concept models of possible solutions to evaluate their merits. Using a decision matrix among other evaluation tools, we selected a slippered design. In the manufacturing stage, we researched various mold-making methods and tried different materials to ensure that we'd have durable layers that would adhere to one another. We also manufactured a mold box and created a half-scale model. In the testing phase, we performed durometer tests to compare the hardness of different urethane rubber samples in contrast with current footshells. We also designed a fixture and determined the appropriate procedures to perform fatigue tests and ensure our product would last.
For our footshell's final design, we implemented 2 layers of different durometer urethane rubbers in a design that would fit our challenger's foot prosthesis in the interior cavity of the shell. We left the toes of the shell solid in order to increase the durability, and also maintained a 1/8 inch thick layer on the bottom of the shell in order to replicate previous footshells worn by our challenger and reduce any discomfort felt when walking, as any change in the thickness of the footshell will require a readjustment of our challenger's prosthesis. For our 2 materials, we chose Vitaflex 40A urethane and PMC 770 urethane, which has a Shore hardness value of 70A. We chose these 2 rubbers as we wanted the top of the footshell to be flexible enough for the prosthesis to slide in easily, while also keeping the bottom of the shell as durable as possible without becoming too stiff. We practiced our chosen manufacturing technique of urethane casting by performing several test castings to determine an initial cure time that allowed the 2 urethanes to bond completely together without any separation. We then constructed a mold box using acrylic sheeting and a silicone adhesive to hold our urethane mold. Modeling clay was used to hold a 3D printed model of our footshell in place, while Vitaflex 40A was poured on top of the assembly to form 1/2 of our mold. After both mold halves were fully cured and the negative was removed from the mold, the footshell was cast by pouring our 2 urethane materials into the mold cavity, 1 urethane at a time.
Getting into the engineering analysis of the project, it was difficult to perform FEA on the footshell due to its complex geometry and inner cavity. The main analysis that was done through FEA was a static analysis of a fatigue test fixture for the footshell. The initial plan was to build the fixture and run fatigue tests to compare to our prototype to an existing model, but we unfortunately weren't able to do this as the quarter transitioned towards online learning. The FEA that was run on the test fixture shows that the geometry of the fixture blades see high stresses due to the large forces placed on them. They'll need to be checked regularly to make sure they haven't been deformed during testing. The test procedure calls for 1 million cycles to be run, which we estimated to be the life that our main user's footshells normally last him for. When we first started pouring and getting our first urethane samples, we performed durometer tests on the samples to compare how hard they were relative to other footshells on the market. We had access to a Shore double-aught durometer tester, but the urethanes we purchased were rated for Shore A hardness, so we used a table to convert the measurements. We found that the samples were slightly less hard than the advertised hardness values, which allowed us to make the necessary changes and order a higher durometer rubber before making the first prototype. The main testing for the project was in fatigue testing, which would directly compare whether or not our prototype had longer life than other foot shells on the market. Although we were unable to start on this testing, necessary steps and procedures to run the testing have been drafted for a future team to possibly pick up in the future.
Our project will hopefully have a continuing impact on future footshell users, allowing them to have shells that will have a longer lifetime. The biggest challenge of this project was creating the right conditions for high-quality pours. We had to make sure the environment wasn't too cold, the two parts of the rubber were mixed thoroughly, and that we rated the right amount of time for it to cure. One major lesson we learned was to keep on top of our deadlines but also remain flexible, as creating the molds would take days due to their long cure time. Not to mention, things are always bound to go wrong. But it was all worth it in the end to bring our concept to life.